I work as a lecturer in glass and professional practice at Plymouth College of Art. As a studio glassmaker, I use traditional manufacturing methods, working molten glass pretty much as it's been made over hundreds of years. I'm no history expert. I'm not a scientist. My background is in the area of art and design, and I'm fortunate to have experienced a huge variety of glassmaking processes and have worked with a number of different glass types over the years. I began my career in 1981 as a craft engineering apprentice at Pilkington Glass in St Helens. I have a degree in three-dimensional design specialising in glass and a master's degree from the Royal College of Art, also specialising in glass. I've recently completed a postgraduate certificate in teaching art, design and communication at the London Institute. I've worked as a lecturer teaching degree students glassmaking and spent 8 years as technical instructor in glass at the Royal College of Art. Perhaps because of my craft engineering background, I've always regarded the acquisition of practical skill to be of equal importance to the pursuit of conceptual artistic endeavour. This is why the work as technical instructor at the RCA suited me so well. It was while I was working at the RCA that I was first approached by Reino Leifs of the V&A and Dr. Sarah Fern of Imperial College in the summer of 2002. Sarah was working in conjunction with the V&A, researching glass conservation using advanced surface analysis techniques in order to find methods of arresting glass disease, the breaking down or corrosion of unstable glass. My work at the Royal College of Art was varied. The philosophy of the RCA, along with most ceramics and glass courses in art colleges, is that ideas are far more important than craft skill. Because of this, I found that 90% of the time I found myself making the work for students to their requirements, not designs as such because much of it was conceptual art. I found that I had to design processes. Therefore, I began to learn a tremendous amount about what glass will and won't do. Glassmaking is a craft. Indeed, any work that involves the performance of a practical skill can be defined as a craft. This would include a surgeon performing an operation, or a scientist performing a practical experiment. The notion of the craftsperson as a quaint or eccentric practitioner is actually a misconception. What links these practical craft skills is the fact that they are tacit. Tacit skill is simply the ability to make well. It's a result of experiencing, production or repetition of making processes and requires training, commitment and time. The word tacit means implied, not stated. As such, it can't adequately be defined in words. It applies to glassmaking perfectly because it's very hard to describe in words what we actually do. A simple example of tacit skill is how we recognize the face of a friend or colleague in a situation where we have a group of people. We can all do it, it's easy, but try writing down factually just how we go about this recognition process without falling back on vague comments like, well, I recognize the face. The result will be a complex document. Now magnifying that complexity by 1,000 and you'll get some idea of what it's like to adequately define a tacit skill such as glassmaking. Now it's important that we recognize the difference between tacit skill and tacit knowledge. Tacit knowledge is far more complex than tacit skill. When a craftsperson, a glassmaker such as myself, is faced with new situations, we reflect on our experiences and use our skill to devise and implement a plan, a hypothesis to deal with each new situation or problem as and when they arise. In short, when faced with new situations, the craftsperson becomes a researcher in the practical context. Through my extremely varied glasswork at the RCA, I've become an expert in how glass works, or perhaps more accurately, how it feels. In order to put the Venetian glass project in context, I think I should very briefly describe how some of the different glass types I've worked with feel to work. Lead crystal is very soft and long working. If it's over 24% lead, it's an extremely forgiving glass, which is why it's favoured by glassmakers like myself with an art background. We can take more risks with a longer working glass. Its main disadvantage is that it's very heavy when working on large pieces. It can be a third heavier than a leadless glass, depending on the lead content. Objects and rims tend to be rather thick, as the glass quickly melts back when it's reheated. We have to reheat the glass to stop it failing due to thermal shock. Soda lime glasses tend to allow the glassmaker to blow thinner objects. It's much shorter than lead glass, and so loses its heat and becomes unworkable very quickly, again the glass will fail due to thermal shock if it gets too cold, so that window of workability is reduced dramatically. The closest leadless glass to lead crystal in terms of how it feels to work with is Gaffer Glass. It looks very good in quality and rather feels like crystal, but is significantly shorter. Philips produces the composition under license, and I find this glass far easier to work with than other glass compositions that I've tried over the years. At Plymouth College of Art, we use Glasma, which is supplied to us by MRJ Furnaces Limited. We use this glass because of the clarity and quality of the finished piece. It's much clearer than any leadless glass I've worked with. Again, like all leadless glasses, it's not as long working as a high lead crystal, so that window of workability is again significantly smaller. As I've said, my past experiences and knowledge of different glass types enabled me to assist Dr. Fern in melting her experimental glass. She had analysed objects suffer from glass disease and recreated the batch composition. Sarah couldn't melt large amounts of glass at Imperial College. She had to pour the glass onto a metal plate, which resulted in small round pellets that had to be ground and polished to produce the completely flat surface needed for surface analysis techniques. Of course, a cold finished surface removes the skin of the glass, which isn't comparable to a blown glass finish. Also, it's extremely difficult to refine glass in small crucibles, even at temperatures reaching 1400 degrees C. What she needed were large, thin, blown plates. I suggested that we put a 25 kilo crucible into one of the furnaces at the RCA. Our first attempt at charging Dr. Fern's glass took place on the 25th of April. The crucible was chosen for its ability to withstand aggressively corrosive glass compositions, and as we can see from the following images, the crucible failed dramatically. The pot was raised for accessibility. The failure was due to corrosive foam on the surface, not the glass itself. The corrosive foam simply ate through the crucible. We followed the manufacturer's recommendations for batch. We put a little in there often, and we took the crucible to 1245 degrees C before we began charging. Now, to be honest, I've learnt over the years that technical recommendations are fine as a starting point, but there are other factors to take into account when charging batch. Most importantly, the amount of glass to be melted and the type of furnace to be used. With the Gaffer composition, Philips recommend a melting temperature of 1350 degrees C and a refining temperature of 1400 degrees C for 1 hour. I've never melted glass over 1250 degrees C, and have melted perfectly good glass at 1190 over 16 hours. This is over 200 degrees less than the manufacturer's recommendations. I got better quality glass when I put most of the batch into the furnace in one hit, and then topped up the level a few hours later. Many glass makers who follow the recommendations have reported flaws in the melt, which are in fact deposits from the pelletized bonding material trapped in layers throughout the melt. I know through experience that working with different designs of pot furnaces, it is in many cases better to reduce the melting temperature and increase the soak time. This reduces the chance of anything going wrong with the melt, such as the introduction of cord, and ensures that bubbles and seed are eliminated, and greatly extends the working life of the crucible. I don't actually believe that the early glass makers had so much trouble with corrosive glass causing pot failure. Wide clay pots would ensure less contact with the walls, so the corrosive foam would be on the surface. Also, because the crucible was quite literally a pot made of clay, it would have to have been glazed with a little cullet poured on the inside of the crucible wall before it was filled with glass. This glaze provides protection from the corrosive foam. It's amazing to think that such ancient technology is far more resistant to corrosion than our most sophisticated refractory materials. So we were left in a position where we had to rethink. I suggested we try again and attempt to effectively glaze the inside of the pot with one hit, putting all the batch together, filling the pot right to the top in one go. On Tuesday the 10th of June we successfully charged 20 kilos of Dr. Fern's batch at 1200 degrees C for 16 hours. It was rather seedy, so we left it for a further 4 hours. After 20 hours it was still seedy, which suggest melting temperatures of 1300 plus, or a soak time of days rather than hours. As we only had a few days to melt the glass and work it, we were running out of time, so I decided to try a cane test to determine the softening point and therefore the safe annealing temperature of the glass. The cane is placed in an annealing oven, leaning at an angle of 45 degrees against the side wall. When it begins to bend in the oven, it gives us a softening point from which we can work out the annealing temperature. I was surprised that I could easily handle the glass at 1200 degrees C, which suggests a working temperature of just under that, about 1180 degrees C. Because of this, I guessed an annealing temperature of about 520 degrees C. I was amazed that the cane slumped at 500 degrees C. More testing gave a softening temperature of 480 degrees C. This in turn gives us a safe annealing temperature of 450 degrees C, remarkably close to that of lead crystal. Now this was quite a shock. It implies a viscosity curve greater than any glass I've ever worked with before. If the working temperature is so high, the annealing temperature should be quite high too, certainly above 500 degrees C. It seems that the window of workability could be as great, if not greater, than that of lead crystal. As we began to make the blown plates that Dr. Fern needed for her research, I finally got the opportunity to feel how the glass worked. It was absolutely brilliant. It seemed impossible to blow the bubble off-center. On one occasion when it did seem to blow off-center, both Dr. Fern and I noted that the glass seemed to correct itself as it was blown. The vessels that I made were thinner than anything I've made before. They bowed in the leer. At first I thought I may have been mistaken with my annealing temperature, or that I was putting the plates in the leer too hot, but they bowed upwards rather than slumped down. It seemed as if they were so thin they warped, like ceramic plates sometimes do when fired. The interesting thing is that when I went back to working with a modern glass that I was used to, and blew a plate for an RCA student, the same thing happened. The plate bowed. My skill level increased dramatically just from the experience of working with this glass. This is an extremely significant fact for someone who works in education. Towards the end of the day, when we made enough plates, we made a few objects to see how the glass reacted. I was amazed to find that as well as being long working, it seemed almost impervious to thermal shock. It just didn't seem to want to break, even when it got ridiculously cold and was then plunged into almost 1200 degrees C in the glory hole. It has all the benefits of each of the glass composition I described earlier, with none of the negative characteristics, discounting the fact that it's so unstable, of course. Because it seems so impervious to thermal shock, it now seems possible for a glassmaker such as myself to take more risks in the making process and recreate some of the incredibly fine, complex Venetian stemware given enough time. I honestly thought that this type of work was beyond me, and that the Venetian glassmakers possessed such skill that I could never hope to match. I'm positive that 17th century Venetian glassmakers were incredible glassmakers because they were working with an incredible glass. Once we eliminate the risk of failure due to thermal shock, we're free to push risks to the extreme, and as I found when I went back to the Gaffer Glass that I worked with and blew my first warped plate, the experience of working with this glass greatly enhanced my level of practical skill. We have to ask why the glass works so well. Workability seems to be right up there with clarity when considering the criteria of quality for this composition. Perhaps when solving the problem of unstable glass types over the years, the workability was affected. I believe that there's a much more simple, important reason that none of our modern glasses seem to match up to this 17th century composition in terms of workability. This glass was developed by a glassmaker. Back then, the craftsperson had the same credibility as a scientist or technologist. In fact, if we go further back in history, we see Leonardo painting the Mona Lisa, producing analytical drawings of the workings of the human body, and designing helicopters in his spare time. There was no difference in the credibility of the artist, scientist, or craftsperson, because they could well be disciplines practiced by the same person. In terms of conceptual understanding, reflective rationality was the only mode of thinking available. This results in a try it and see kind of research. Since then, art and science have separated and become two very different disciplines, which in turn require equally different kinds of rationality. During and after the Industrial Revolution, production has increased massively, and so complex administrative systems have had to be introduced. In society as a whole, technical rationality has replaced reflective rationality in the way that we think. The most crucial aspect of modern technical rationality is that administrative and political change is decided outside of the working environment and handed down the chain of management to the practitioner in the form of instruction or training. The most significant aspect of reflective rationality was that any change was made within the practitioner's working environment. Solutions to problems were found in the glassmaker's working environment inside the context in which the problem arises. These days, every person who works in large organizations have to have their role defined. It's very easy to define the role of a scientist or technology in words because the nature of these disciplines concern definitions and proven facts. But as I said earlier, tacit skills, such as those belonging to a glassmaker, cannot be articulated easily into words. As such, it's impossible to define the glassmaker's role adequately. The problem is, once we attempt to make a system transparent, we must try to define it in order for it to be understood. As it's impossible to articulate the tacit elements, what is left is only what can be adequately described. The tacit elements, those vital ingredients that are needed to achieve quality in anything that we do, are lost. As the influence of science and technology has been enhanced over the years, the influence and therefore the credibility of the craftsman has diminished. As it's impossible to articulate the tacit elements, what is left is only what can be adequately described. The tacit elements, those vital ingredients that are needed to achieve quality in anything that we do, are lost. As the influence of science and technology has been enhanced over the years, the influence and therefore the credibility of the craftsman has diminished. These days, the vast majority of glassmakers work in factories. Within the conceptual framework of technical rationality, they are perceived to be working on a low level of theoretical knowledge and are merely following instruction from the managerial and administrative power structure above them. The introduction of technical rationality into modern society has created a complex hierarchy of managerial responsibility. The trouble is that within these power structures of large companies and organizations, we confuse this hierarchy of responsibility with a hierarchy of credibility. As the glassmaker's credibility diminishes over the years, the issue of workability becomes a less important factor to those who decide on the glass composition. Clarity, the elimination of defects in the glass such as cord, seed and bubbles, and of course sourcing of materials and cost, have over the years become far more important criteria than how the glass feels to work with. The credibility of the craft practitioner is diminished further when we consider that within the subject of glassmaking, most universities and colleges are no longer interested in teaching advanced practical craft skills or glass technology. As art and science have separated over the years, a similar thing has happened with art and craft. Students studying glassmaking, usually within ceramics and glass BA and MA courses, are primarily engaged in the production of conceptual art. The philosophy within these courses is that ideas are more important than skill. In fact, skill is looked down on because it's seen as restrictive to the creative process. Of course, there will always be gifted students that make their own hot glass pieces. Samantha Sweet and Carl Norberg are just two examples that have attended the master's course at the RCA. But each of these students have spent years experience in production manufacturing in a professional environment before they came to that college. They already possess their considerable craft skill. The plain fact is that it's impossible to teach a craft skill on a BA or MA course because of the intellectual framework of the course itself. The whole purpose of these courses is to produce self-motivated learning. Indeed, this is the main criteria for assessing BA students. When we try to teach a skill such as glassmaking in this environment, we must engage in teacher-led learning activities. Because this is the way they were taught at school, the students feel as if they're taking a kind of theoretical step backwards. As I found when I worked at the RCA, most of them would rather have a craftsperson make the work for them. This further undermines the credibility of the craft practitioner. After years of art education with all my courses and qualifications, no one ever taught me anything about glass technology. I'd never questioned the quality of my art education in terms of artistic development, but I am beginning to question the relevance of an applied art that seems totally involved in the pursuit of conceptual expression. I also question the relevance to society of applied art that rejects the need to teach advanced skill in higher education. I find the notion of applying art to art absurd. Just as I knew little about glass technology, Dr. Fern had never had the opportunity to gather molten glass and feel what it's like to work with before we began to work together. Science uses technical rationality as the preferred mode of thinking. Art, particularly involving a tacit crafts such as glassmaking, is one of the few areas of Western society that still uses reflective rationality as a preferred mode of thinking. Neither Dr. Fern or myself could have achieved these results that we did alone. Only by bringing together the two areas of art and science can we get close to how people from the 17th century and beyond actually thought. Even if we've written evidence from the past, words convey meaning to the reader based on their own experiences, not the actual experience of the author. As such, these words and their meaning are open to interpretation. If we conduct historical research based on our preferred mode of thinking, that of technical rationality, our findings could be flawed due to the fact that our conceptual framework didn't actually exist at the time that we are researching.